micron feature size. We also can fabricate the CMOS chip or superconducting chip. We have a foundry process, and then we can assemble two together. With our process, we regularly delivering 35 micron pitch flip chips, and maximum chip size is about 100 millimeter square. We can do in-house testing, RF and DC test, and also we can do module level testing. But in most of our cases, we send the final product to the collaborator, and they do the final module level testing. Here's an example. Is an SMCM design, and then you fabricate the SMCM and then bump the MCM and then bond with multiple chips. Here's a 16 chip MCM where we put 16 5mm by 5mm chips. It's called JJ chip, and the junction size ranges from 500 nanometer to 1500 nanometer. And here we bond one chip at a time. And what we found, this is the fabrication or attachment process over here, that you start with MCM wafer and then bump the entire wafer, and then you dice in individual MCM and bond with multiple superconducting chips to create multi-chip module or system in a chip. We are using indium bumps over here because it produces very, very low resistance in the range of nano ohm. It's ductile in nature, cryogenically stable, and the melting point is about 157 degrees Celsius, which is good enough for MCM reflow process. The advantage of our attachment process, we are depositing indium only on the MCM side. So this gives us ability to select the known good chips from various suppliers, because you're not putting bump on the chip side. Or in other words, you also have a possibility to combine multiple chips fabricated in different foundry process and combine all the chips together to the MCM and create next generation system in a chip or multi-chip module. We have studied the junction's behavior with flip chip process, and what we found that room temperature study shows that the junction's resistance is basically in the same range which is expected for different size of junctions. So we didn't see any degradation with room temperature study. And then we did also cold testing, where we found the typical cold IV plot for individual junctions. And also we have a series of 9,000 junctions, and we have tested with a control chip. Here control chip is basically neighboring chip of the same wafer, and we did characterize cold testing, and the IV characteristics is pretty much same with the control chip, which indicates that flip chip process is not degrading tri-layer junctions. Next, move on to a qubit process, flip chip process, and again it's the same process like SMCM attachment process. You start with a interposer wafer, bump the interposer wafer, and then you align with qubit chip and bond it to create flip chip qubit. We did a lot of flip chip characterization for flip chip qubit. This is very, very important. I'll tell you in the next slide. So the alignment, bonding, and parallelism is very, very important for flip chip qubit. We have used confocal microscopy to understand the coplanarity of the chips. And what we found in most of the cases, that coplanarity of the flip chip is within the TTV limit of the top chip, which is really, really good for flip chip qubits. We did use X-ray to understand the bump deformation, how much deformation we need. So it's also critical to make sure that you are not creating electrical shorts. We're using IR microscopy to understand that alignment accuracy, and we are maintaining within plus minus 1 mic accuracy. And this alignment is very, very important. Why? Because here's the design features. Here you can see a qubit loop which is in one chip and bias loop which is on the other chip, and there is a design offset. In one case the loops are within minus 1 micron overlap, and in other case there is a 0 micron overlap over here. And you can see we can maintain such a tight design tolerance in the Z directions, and that can help us to maintain qubit performance. Here is again an animation of flip chip process. So here is your qubit chip and here is your interposer. So qubit chip will flip and bond to the interposer. Some key flip chip bonding parameters we need to establish. One of them is to see the proximity surface impact. So we put a silicon chip on top of qubit chip and we didn't see any qubit performance degradation. We also produce a very low interconnect resistance in the range of nano-ohm. We also demonstrated capacitive coupling as well as inductive coupling between qubit chip and interposer. These are the key demonstration for creating 3D structures. Not only that, we also did some apples to apples comparison. So here's the design. In one design, qubit, bias line, readout resonators all are on the same chip. On the other hand, the flip chip qubit has readout resonators and bias lines are on the interposer chip. And then we measured the qubit performance, which is basically the coherence time, and we found the coherence time is in the range of 20 microseconds, same or similar for both cases, which is a typical value for this kind of design. So we have demonstrated flip chip qubit, we have demonstrated flip chip MCM, we are making superconducting TSV, interposer with superconducting TSV, and these interposers are about 200 micron thick. So the TSV has critical current above 20 milliamps, which is more than sufficient for qubit operations. Now let's move on to some 3-stack bonding. Again, this is an animation you can see over here. So first you attach interposer and then you attach the qubit chip. And we have made many mechanical samples to understand the cross section, basically bump deformation, and also we did some coplanarity study, and what we found over here, even with the mechanical sample and 3-stack bonding, we still could maintain the coplanarity within the top chip TTV limit, which is really good for 3-stack samples. Now let's compare superconducting packaging with semiconductor packaging. For superconducting, we are making a very complex wire bonding structure. We're making flip chips, we're making 16-chip MCM, which is very complex. We are also evaluating 3-stack bonding, and in future we're planning to do 3-level of assembly and also rigid flex architecture for next generation packaging. On the other hand, the semiconductor industry, every year you will see a new type of package coming up. So it's very difficult to remember all the names. But what I would like to tell you, I'm categorized the most important packages. One is, for example, system in a package or multi-chip module. Other one is package on package, package interposer package. Then wafer level package or chip fast proc package or redistributed chip packaging. Then 2.5D technology, and then 3D or HBM technology. So what I'm comparing is basically the microbump approach for 2.5D with MCM. So microbump process for 2.5D technology generally use copper-based, copper pillar with solder tip, copper to copper or high melt solder material, but in our case we use indium. The microbump pitch is 45 micron or less. We are also using 35 micron pitch, which is very comparable. The number of microbump assembly for 2.5D technology is 1, but they do use C4 and VGA assembly. In our case, we do 2 level of microbump assembly. The maximum chip, 5 chip they are using right now, but the chip size is way bigger than 5x5. But we have demonstrated so far 16 chip with 5mm by 5mm chip. Interposer size can use 750mm square. Again, this is limited data. Nowadays probably it's using way bigger than that. We can go maximum 1600mm square. The feature size is 0.4 micron because it's a 65 nanometer technology node. We can go up to 0.8 micron because we're using I-line lithography. So I don't want to compare really apples to apples comparison. So we are over here with 2.5D technology. 2.5D technology is a very mature technology, and there's a lot of work going on in this direction. So like whatever I'm claiming over here, maybe it's already a lot finer pitch is already demonstrated. But what is our goal over here is that we would like to go a similar type of microbump technology in superconducting packaging, so that in future, if there is a hybrid architecture comes with superconductor or semiconductor chip together, would be a lot easier for us to combine these two structures together to create next generation and computing architecture. At the end, let's take a look into the future. So here's the future, how it's look like. We are making a very, very complex 16-chip MCM. We are evaluating 3-stack bonding. We are producing very high-quality qubit chip. We already demonstrated off-chip coupling, superconducting TSVs, also producing very high-quality traveling wave parametric amplifiers and superconducting indium bombs. So next is combine this all structure together to create a 3D architecture, and then at some point integrate that 3D architecture to the rigid flex configuration to create next generation quantum computing hardware architecture. With this, I would like to summarize my talk. An integrated approach to develop 3D construction on various split chip qubit package configuration is demonstrated. Demonstration of key flip chip building blocks offering solutions towards 3D cryogenic qubit integration. And the last point is rigid flex technology may be attractive for connecting superconducting qubit to the classical electronics.
Hello, my name is Paul Franzon. I'm professor at North Carolina State University. I'm honored to be invited to be on this panel, and I hope that you are all safe and well. I'm going to be talking about applications of quantum computers in electrical engineering. And this is work that I've done with two students, Isaac Turteltaub and George Lee. This is an outline of what I'm going to present. I'm going to go through some of the basics of quantum algorithms and quantum computers before talking about their limitations, which motivates us to look at variational algorithms and programs and using those to solve problems of interest to us. And I'm going to specifically introduce VQE, which can be used for graph optimization problems. I'm going to discuss VQE and its application of VLSI placement before briefly outlining future work. The beauty of quantum computing is that you can achieve quantum parallelism through superposition. That is, in the classical world, the spin of an electron might be spin up or spin down. We'll call this 0 or 1. In the quantum world, the spin of an electron is a superposition of these two states, and that superposition is actually in a complex mapping. So when you take a classical qubit and apply a superposition step, you then turn it into the quantum qubit, on which you can do various operations, including entangling it with other qubits. That is, if you end up measuring the qubit, you know what the value of the other qubit is, and rotations in the complex space. That is, illustrated here was what's called the block sphere. If they're in the state 0, we're pointing up. State 1 is pointing down. The superposition of the two states, an equal superposition of the two states, brings you onto this dotted axis, this dotted circumference of the block sphere, in either the real domain or the complex domain. And you can apply arbitrary rotations to bring it to the state vector to different locations on this block sphere. And these rotations are a part of the quantum computing algorithm that's actually run. As I mentioned, you then do a measurement which collapses the superimposed states back to one of the two classical states. The probability of it being in state 0 is alpha squared. The probability of it being in state 1 is beta squared. Thus, the beauty of quantum computers is that n qubits require 2 to the n coefficients to describe them. So that means you've got an exponential space of values that you're computing based on n bits. And this gives tremendous inherent parallelism and the potential for solving problems in real time that are not otherwise solvable. So let's look at a simple quantum computer program. I won't be going through this in detail, but the idea is you set the qubits into some initial state. You then perform a set of operations on those qubits. In the mathematical realm, these operations can be considered as tensor operations. That is superposition, various rotations, entanglement. And then after performing those steps, you do a measurement step. In the measurement step, the qubits collapse back to 0 or 1 with a probability of alpha squared and beta squared. And thus, if you run this quantum computation many times, you work out the probabilities of the qubits ending up in state 0 and state 1. And one aspect of quantum computers is that the steps are reversible. Now, I'm not going to go more into how quantum computers work. I'm sure other panel members did that. But there's some practicalities in this that lead to the choice of algorithms to run on a quantum computer. First one is what's called quantum volume is limited. This is because the coherence time in which the qubits stay in their entangled superimposed states is limited. Quantum volume is characterized by the number of qubits times the number of steps. Quantum computers are noisy. That is, you won't get the same value every time you run it. If you're measuring a probability, you run it multiple times to get around this issue. But there are some applications of quantum computers where you want exact answers. So you either need massive error correction to enable those, factorization is one of them, or you need the ability to cope with errors. Measuring probability is one approach to that. Variational algorithms is another approach to that I'll describe in a moment. Current quantum computers have limited interqubit connectivity. Since entanglement requires connection between the qubits, then this means that it slows down entanglement. It can take many steps to enable entanglement on a quantum computer with limited interqubit connectivity. So what we're entering now is the near intermediate scale quantum computer era, sometimes referred to as the NISQ era, where we're going to have 100 to 1,000 noisy qubits, and the challenge is finding applications that can run on NISQ quantum computers that are interesting and demonstrate superiority over applications run on classical computers. And I believe that the problems that we're looking at have the potential to deliver on that promise. There are three basic classes of quantum algorithms. There are quantum algorithms that are gate circuits, that is, they're purely quantum. I illustrated this a little while ago. Essentially a series of tensor operations on the qubits, but with the inherent parallelism given by superposition. Examples of such algorithms include factorization, Grover search, and quantum Fourier transform. There are annealing algorithms where you find the minimum energy of a set of states. These quantum computers, for example, D-waves, can be quite large, and there are interesting problems that can be addressed with those. But the D-waves computer in particular doesn't allow entanglement. And what I'm going to introduce here are variational algorithms that deal with the randomness and noisiness of quantum computers directly. Examples are autoencoders, eigensolvers, classifiers, quantum optimization algorithms. Sometimes these are also referred to as quantum machine learning for reasons I'll explain in a moment. So variational algorithms are run on a hybrid of a quantum computer and a classical computer. On the quantum computer, we execute a gate quantum algorithm as described earlier. We present a state vector at the front here. We do a set of operations, and we use those to calculate the energy of the system. if we do, and then what we do is set the parameters of the state and the operations to try to allow us to explore and find what parameters give us the optimum energy. That is, we go through this loop many times to build up a map of the energy, so on the vertical axis, versus the parameters, which are on the horizontal axis. And this, of course, being more multi-dimensional than what I've shown here. So initially, you don't know what this energy map looks like, but you do multiple quantum computations to explore what set of parameters lead you to the optimal energy state, and that optimal or minimal energy state allows you to solve an optimizational problem. So a quantum computer generates variational states. A classical computer is used to find the parameters that give the optimum energy of the system that's being modeled. The reason this is called quantum machine learning is because, like machine learning, you learn from the data rather than some underlying physics. We're doing the same thing here to some degree. We are running the quantum computer, which generates somewhat random information, and using that data to find the optimal solution, much like you use the data to find the optimal solution in machine learning. One specific algorithm that we found very useful is variational quantum eigensolver. This was originally designed to estimate the ground state of a molecule or any multi-atom system. This is a very useful algorithm, and what we're doing here is we're actually using the quantum computer to model a quantum system. And then we change how we represent the system to model a problem of interest to us in electrical engineering, in particular graph optimization problems, as you'll see in a moment. So the objective is to find the state with the minimum energy. And what VQE does is find the eigenvector with the lowest eigenvalue. This runs much like I described in the previous slide. We present a quantum state, including a set of angles for rotations, to the quantum computer. That goes through a set of gate functions to capture the situation that's being modeled. We then do a set of measurements. We get energy from that, and then we explore the energy versus parameter space in the classical realm, so that we try to find what set of parameters give the minimal energy solution, or the ground state. We do this iteratively, feeding back parameters to, particularly these rotation angles, to the quantum computer. Here's a reference that explains this in technical terms, but in a way that I believe is understandable. VQE can be applied to many optimization problems, including min-cut and max-cut on graphs. The way this is done is, instead of using the quantum computation steps to model a molecule or a set of atoms, we use it to model a graph. That is, the nodes are the qubits, the edges, and whether they're present or not, are encoded in the quantum computation steps. We think of the qubits as colors, and we find the equal partitioned min-cut graph as the minimum energy solution. Here, the minimal cut graph has a cut, where I'm dragging the cursor right now, between the two different colors, and this is the minimum cut solution to this graph problem. So again, what we're doing is taking an algorithm that is designed to model a quantum computing system and instead use it to model a graph and find the minimum energy solution, which happens to be the minimum cut solution. So this leads us into applying quantum computing to problems in electrical engineering. There are many electronic design problems that are graph optimization problems. I'll give one in a moment. But the algorithms to find exact solutions to these optimization problems are usually NP-hard or NP-complete. That is, that to run the exact algorithm that's going to find exactly the best solution is going to take too long to run. So instead, what we commonly do employ heuristic algorithms which use some approximation or some simplifying step or a greedy algorithm to do an iterative solution that does not give the optimal solution, but gives us one that has been useful in electrical engineering problems today. And what the anticipation is here, that we can instead use variational quantum solvers to find near exact solutions that are actually better than the one found by the heuristic algorithm. So here is one such problem, VLSI placement. This is placing a set of logic gates on the surface of a silicon chip so as to minimize the area and meet timing, and to minimize power consumption. So one way to formulate this is to find the location of each logic gate on the silicon chip that minimizes the total wire length connecting the gates. That is, where to put, is a simple problem, where to put these 6 gates so as to minimize the total length of the wires connecting the 6 gates, thus minimizing the area, the power, and the timing. One way to solve this is with repeated min cut. Here's an example. Again, here's my simple 6-gate circuit. I want to start assigning gates to areas of the chip. The balanced min cut is shown here. 3 gates on the left of the cut, 3 gates on the right of the cut. The balancing is important. And we only cut 3 wires, so it's the balanced partitioned min cut. We then apply that to the physical domain, where 3 of the gates are put above the cut line, 3 of the gates are put below the cut line, and thus we start iterating on our placement. We then do another balanced min cut in each of the subdomains and keep repeating that until we've assigned each gate to a specific location in the global floor plan. Now, this is commonly solved with a heuristic placement algorithm. Kernohan-Lin is one such algorithm. It's a greedy algorithm that does a set of swaps to try to minimize the total wire length, but it's not an exact algorithm. It doesn't give the exact optimal solution. It's a heuristic solution that we run for long enough that we can run in linear time in order to sort a graph into 2 subgraphs. So here what we did is we programmed admittedly a quantum computing emulator to run VQE on this gate represented here. This gate netlist represented here, which corresponds to this graph here. We're just doing one step in the placement algorithm at this point to find the first initial balanced min cut, and that is between the 2 different colored vertices, 2 different colored nodes. As you can see, that we have 2 cuts separating 4 gates from another 4 gates, and this will give us the first step in the placement. We also ran Kernohan-Lin on the same problem, and that did not find the optimal balanced min cut. Yes, it found a balanced cut with 4 gates on each side, but there are actually 3 edges crossing the boundary between the 2 sets of gates. So this won't be the optimal first cut. And thus we've actually demonstrated, at least on a quantum computer emulator, that we can use VQE to start getting better solutions than Kernohan-Lin can give. So that's the start. We're at the moment iterating on the solution on the previous page to actually get a placement, and we're actually starting to apply it to larger problems. But these are still toy examples. where actual fact the NP hard solution would actually take a reasonable time to run. Question is, what can we do with a 1,000 qubit machine? And can we use it to address real-world problems where we have, say, 1 million gates or 1 million nodes that we want to solve? What we're investigating are hybrid algorithms between the classical algorithms and the quantum algorithms that can map and solve a large problem on a NISQ 1,000 qubit machine using, was one of its underlying steps, VQE. We're also investigating other design problems that lend themselves to being solved in this fashion. And a key step in this work, which is actually in the algorithm domain, is to identify and investigate better optimizers, because as these problems get larger, we're choosing amongst many, many angles, and we want high quality optimizers that can deal with high dimensional spaces. I thank you for your attention. Before I let you go, I will acknowledge funding by National Science Foundation and the NCSU IBM Q Hub membership. I again acknowledge the students whose work I'm essentially presenting, Isaac Turtletub and George Lee. And if you have any questions for this panel, please contact me. I've left my email here. And I thank you again for your attention, and I wish you good health in the rest for the pandemic. Thank you very much.